All right, ladies. So on Tuesday, we started a new unit, and it's called Kinetic Molecular Theory, and it's also going to be covering gas laws. And so what we're going to do today is lecture to make sure that you understood the things that you discovered through those PhET simulations, through that web quest that you did on Tuesday. And I kind of like this unit because you're going to get to see some everyday applications to the things that you're learning in chemistry class. And I know lots of times y'all feel that there isn't a whole lot of useful information coming from your chemistry class, but I promise you for this unit, you're going to have that chance to see some everyday applications. All right, so let's get started. So, if you're in your bedroom and you have one of your parents cooking dinner, how long does it take before you smell the food? And why don't you smell the food immediately as it's being cooked? And for those of y'all who maybe are upstairs, clear on the other side of the house from the kitchen, it takes a lot longer for you to get the smell of the food being cooked. So we know that gases, that's what we're talking about here, they do travel, and that the more space that they have to move in, the longer it can take before you smell that odor. And this maybe is even more evident to you if someone's wearing perfume. If you're standing very close to them, you can smell that perfume. But if you're on the other side of the room, hopefully they haven't put on so much perfume that you can still smell it. But so usually gases, they're going to take a little while to travel, and the more space that they have to travel in, the longer it is before there is evidence that that gas has traveled. That evidence is usually for you and I when we can smell it. So instead of saying kinetic molecular theory over and over again, you're going to hear me talk a lot about KMT. And KMT is based on the idea that particles of matter are always in motion. Now, kinetic molecular theory can be used to explain the properties of all three states of matter, solids, liquids, and gases. But what we're going to focus on is how KMT can be used to explain gases. All right, let's go ahead and talk about kinetic molecular theory's 5 assumptions. So this theory on the movement of particles is based on 5 assumptions, and it's important that you know what these 5 assumptions are. First of all, and remember, what we're doing with kinetic molecular theory is that we are focusing it on gases. So gases consist of large numbers of tiny particles that are as far apart relative to their size, so that most of the space that a gas occupies is actually empty space. The collisions between the gas particles and between the gas particles in the walls of their container are elastic collisions. So what does that mean? In other words, there's no loss of total kinetic energy. There's no loss of energy as these particles bounce off of each other or bounce off of a wall. Now, this is an important assumption because usually what we see, like if we take a bouncy ball and we drop it on the ground and we watch that bouncy ball bounce, we're going to see that as it continues to bounce, it bounces a little less and a little less and a little less, just like we see here on the picture to the right. So KMT is based on this idea of elastic collisions, that there is no loss of kinetic energy as these gas particles hit each other and bounce or hit the walls of their container. And gas particles are in a continuous, rapid, random motion. They move in straight lines. They're moving very quickly. And they possess kinetic energy, which is the energy of motion, as opposed to potential energy, which is the energy of position. Assumption number 4, there are no forces of attraction between the gas particles. So when these gas particles hit each other, there will be no bond, no intermolecular force that will form between them. They're going to hit each other, bounce off of each other, and not be attracted to each other at all. Assumption 5 is that the temperature of a gas depends on the average kinetic energy of the particles of the gas. So remember, temperature is always about average kinetic energy. That's the definition of temperature. The formula for kinetic energy is 1/2 the mass times the velocity squared. Now, ideal gases, which is what we're going to be talking about for this unit, is a very hypothetical gas whose pressure, volume, and temperature behavior perfectly fits all the assumptions of the kinetic molecular theory. So what are some of the properties, characteristic properties of gases? And one is that they expand. Gases do not have a definite shape or a definite volume. They just take up whatever shape of the container, whatever size container they are given. Gas particles move rapidly in all directions. Okay, so that goes back to kinetic molecular theory, assumption 3, without significant attraction between them. There you go, assumption 4. Fluidity. So gases are actually considered to be a fluid. Just like liquids are considered a fluid, gases are considered a fluid as well. Because the attractive forces between gas particles are insignificant, gas particles glide easily past one another. And because of this flow of these gas particles, that's why we consider gases to be a fluid. Low density. The densities of a gaseous substance at atmospheric pressure is about 1/1000th the density of the same substance in the liquid or solid state. So because so much, remember, density is mass over volume, and because so much of that volume is empty space, that's why we get such low density for our gases. They're very compressible. During compression, the gas particles, which are initially very far apart, are crowded closer together. And diffusion. So once again, we're getting back to that idea of smelling cooking smells or smelling perfume. Spontaneous mixing. So diffusion is the spontaneous mixing of the particles of two substances caused by their random motion. So gases spread out and mix with one another even without being stirred. And the random and continuous motion of the gas molecules, going back to KMT, assumption 3, carries them throughout the available space. All right, so let's talk about kinetic energy and temperature. All gases at the same temperature have the same average kinetic energy. At the same temperature, your lighter gas particles have higher average speeds than your heavier gas particles. Once again, you got to see this in your KMT web quest with the PhET simulations that you did on Tuesday. And so you even had on the bottom right of your screen, you had a little plus sign where you could either work with a heavy particle or a light particle. And so you could see that those lighter particles moved much quicker than the heavier particles. So this also, when we're looking at the periodic table, we're going to see that our lighter gases like hydrogen are going to move much quicker than our heavier gases such as oxygen. All right, so we've been talking a lot about temperature, and this would be a good time to make sure that you understand that there is a difference between heat and temperature. So heat is a form of energy. It's a form of kinetic energy. And the heat and the amount of heat that a substance or gas particles have depends on the speed of those particles, the number or of particles that you have, and the type of particles in the substance. Temperature, on the other hand, is about the average of the energy. And the temperature doesn't depend upon the size or type of object. Temperature is a measurement, and you are measuring the amount of energy or the average amount of energy, in this case heat, that substance has. Heat is not a measurement. Temperature is how we measure heat. So heat flows. Heat and energy are really very interesting. If you decide to, let's say, be an engineer, you can take a whole class studying the movement of this energy because it is really, really interesting. So temperature indicates the direction of heat flow. And heat is always going to move from a hot object to a colder object. So it always goes towards, heat is always going to go from those that have more disorder, where in disorder I'm talking about the particles and the particle movement. Remember, the more particle movement you have, right? That's what kinetic energy is particle movement. The more heat you have, and that is going to be transferred. It's almost like a domino effect, okay? Once you add heat energy to one particle, it will continue to be transferred down the line, as it continues to find other particles that don't have as much energy as that first original particle has. So we see this once again. Hot cup of coffee it's hotter than your hand, so you feel that in your hand. You feel the heat. There's a transfer, there's a flow of heat from the cup to your hand. Now, the opposite, if you have a cold glass of iced tea, your hand is much hotter than that cold glass of iced tea. So heat will be transferred from your hand to the cup. This is what makes those insulated Yeti cups and hydro flasks that so many of y'all like keep the drinks cold for so long, is because it really does limit the amount of heat transfer that can happen from the air outside of the Yeti cup, or the amount of heat that you have in your hand, to the drink inside of it. And temperature. So we've been talking about how temperature is a measurement of heat. And there are 3 different ways that we can measure temperature. And as Americans, we do have to be almost trilingual because we measure temperature in the Fahrenheit scale, while the vast majority of the rest of the world uses the Celsius scale. And then on top of that, the scientific community uses the Kelvin scale. Now, I do want to point out to you in this graphic that you have here in your notes that this, make sure this is working, this sign here, that little degree sign next to the Kelvin, should not be there. We do not use, we don't say, and we do not write degrees Kelvin. We just simply say kelvins, and the symbol for it is a capital K. Um, and so what you are responsible for in chemistry class is understanding the Kelvin scale and understanding the degrees Celsius scale. And let's see. So in order to, you need to be able to Celsius to Kelvin and Kelvin to Celsius. Celsius to Kelvin, add. And what is it that you are going to add? You're going to add 273.15. So think of it this way. Celsius Kelvin, add. CKA. If you need to go from kelvins to Celsius, you're going to have to subtract 273.15. So this one you can say Kelvin to Celsius subtract KCS. Now absolute zero is a really interesting phenomenon. This is the lowest possible temperature where nothing can be any colder. No heat energy remains in the substance at all. There is zero movement of those particles, of those atoms. And absolute zero has, I guess you could say from a high school level, it has been obtained. They've done it in outer space where it's already pretty cold to begin with. And some really interesting phenomena happen when you get particles to absolute zero. I don't know if y'all remember from the beginning of the school year when we talked about Bose-Einstein condensates. That is the type phase of matter that you can gain once you get atoms to absolute zero. So also you are responsible for being able to convert Celsius to Kelvin and Kelvin to Celsius. Yes, this does mean that you need to memorize 273.15 and whether to add it or subtract it. All right, let's look at pressure. Pressure is the force per unit area on a surface. So force over area. Now, I'm not going to have you work problems per se in like this. You will be responsible for doing some pressure conversions, but not necessarily using this formula. But I wanted you to see it so that you could understand the relationship. What we have here is a ballerina, and we can see in the first picture to the left that she is standing on both feet, and the pressure that she's exerting onto the ground is only 1.5 newtons per centimeter squared. But notice once she stands up on her toes, and there is much less area of contact, the toes is a much smaller area than the entire feet, we see that that pressure goes up considerably. And then when she only stands on one foot, on one toe, we see that that pressure goes up even more. So as the area of contact decreases in size, pressure increases. So we see an inverse relationship between pressure and area of contact. So gas pressure, so let's go back, now that we talked about it in that regards, let's go back to talking about pressure in terms of gases. So gas pressure is caused by collisions of the gas molecules with each other and with surfaces with which they come into contact. The pressure exerted by a gas depends on volume, temperature, and the number of molecules present. The greater the number of collisions of gas molecules, the higher the pressure will be. Which, once again, we have some pictures here that's very similar to our dancers. High heels, especially the very, very spiky high heels, will put a lot of pressure onto the ground. In fact, very spiky high heels can even dent wood floors. Whereas, let's say, the very big feet of an elephant, even though we have this very massive elephant, because they have 4 feet, they are all very large feet. This elephant would probably be exerting less pressure on the ground than this woman with the spiky high heel on. And this is the same phenomenon behind snowshoes. Not that too many of y'all here in Louisiana have a lot of experience with snowshoes, but it's the same idea. If you can get the pressure to go over a larger area, the whole snowshoe, the less chance you will have of sinking into the snow. All right, so how do we measure pressure? A barometer can be used to measure atmospheric pressure. The barometer was first made by Evangelista Torricelli in the early 1600s. As the name implies, he was Italian. And here's a picture of a very simple barometer. So he took a very long tube, glass tube, and he put mercury in it, flipped it over, and he had mercury in a bowl as well. And what happens is that as the air pressure pushes the mercury, so remember Hg is the elemental symbol for mercury. So as the air pressure pushes the mercury in the bowl down, the mercury will move up the tube to a height of approximately 760 millimeters. And that will let you know what the atmospheric pressure is for where you are. Now, we'll get to this in just a moment, but atmospheric pressure will change depending upon whether you're at sea level or if you're up in the mountains. Or even better, if you're diving, I don't know if any of y'all scuba dive, but you will feel a considerable amount of pressure the further down you go in the ocean. Please feel free as you're looking at your notes and taking notes as you're listening to this screencast. Please feel free to stop the screencast and watch this video on how a barometer works. Now, we actually have a lot of different units for units of measurement for pressure. Okay, we have the Pascal, and Pascal, actually it's the kilopascal, small k, capital P, small a. That is the actual scientific unit for pressure. You also have millimeters of mercury, mmHg. You have the torr, obviously named after Torricelli. Atmospheres. Probably a lot of y'all have heard of atmospheres of pressure if you watch the weather, especially when there's a storm coming, even like a hurricane. The atmospheric pressure, you'll hear the weathermen talk about the atmospheric pressure dropping. And one of the things that we know is that as the atmospheric pressure drops more and more, the stronger the hurricane is. And then pounds per square inch, PSI. So lots of times your bike tires, your car tires, the amount of air pressure that should be in those tires is measured in PSIs. Now, in this classroom, you are responsible for being able to convert from one unit of pressure to another one. You are responsible for atmospheres to millimeters of mercury and vice versa, and atmospheres to kilopascals and vice versa. So what I thought we should do is go ahead and work a couple of example problems with this, so you can see how this works. All right, so when you go to solve these problems, you're going to do a setup very similar to your stoichiometry. In other words, you're going to be using railroad tracks all over again. Once again, what we see here is that we have a known value. So our known is 738 millimeters of mercury, and our unknown, what we're solving for, is what is that measurement in atmospheres. So I'm going to go ahead and put 738 millimeters of mercury. And then this here is going to be the stuff that you need. That one and this one. These are your two conversion factors, and I'm going to go ahead and put that in red. That are going to be the stuff you need to memorize right there. All right, so from looking at those conversion factors, we can see that there are 760 millimeters of mercury in 1 atmosphere. So clearly we have a division problem here. So you're going to do a little bit of punching and crunching, and you should come up with 0.971 atmospheres. There we go. Notice that my final answer has 3 significant figures, just like my known value has 3 significant figures. And I also put my unit, atmosphere, behind it. And then last but not least, I am going to box my final answer. All right, let's look at the next problem. And make sure we have enough space. All right, so for this one, it says that the air pressure in a tire is 2.38 atmospheres. What is this pressure in kilopascals? So once again, our known is 2.38 atmospheres, and our unknown is what is that value, what is that 2.38 atmosphere equal to in kilopascals. So same thing going on here, just a little bit of a train track. 2.38 atmospheres. And we have a different conversion factor we're going to use here. So in 1 atmosphere, we have 101.325 kilopascals. This conversion factor always reminds me of a radio station, 101.325, and that's kind of how it helps me to remember what the value is. So once again, if you go ahead and punch and crunch that, you will see that you should come up with 241, oh, come on, there we go, kilopascals. Notice once again, our known value had 3 significant figures, so my final answer also shows 3 significant figures. And then box your final answer. So, so far that's the math that you're responsible for, your ability to convert temperatures between degrees Celsius and kelvins and degrees Celsius. So your magic number, your conversion factor for that is 273.15. And then you have these other 2 conversion factors that you need to memorize as well, to be able to go between atmospheres and millimeters of mercury and atmospheres and kilopascals. So there's your conversion factors there. All right, let's keep going. So pressure and temperature have a direct relationship. As your temperature increases, the pressure will increase as well. If your temperature decreases, your pressure will decrease as well. So I don't know how many of y'all remember back from freshman year, the physical science teachers gave you an extra grade assignment to do at home where you could take a balloon, blow it up, and tie a string around it, and then put that balloon into the freezer. And I think you had to wait, a couple of hours to make sure that the air, the gas particles inside that balloon got cold enough. And when you took out the balloon, you could see that it shrunk because the string was no longer tight around the balloon. There was usually an inch or two of extra string, I guess you could say, compared to the size of the balloon. So as temperature increases, pressure also increases. As temperature decreases, pressure will decrease. This can also be seen with a Coke can. If you have a 6-pack of Coke, and it's a hot summer day, and you leave that Coke, those cans of Coke, in, let's say, the trunk of your car all day long, there's a really good chance that that Coke is going to explode, because as that carbonation, that gas inside the liquid, continues to get hotter and hotter, the pressure will increase until the cans pop. And why is it that the can is having to pop? Because the volume of the can could no longer take the pressure that was inside, the internal pressure, and so the can eventually pops. So, speaking of internal versus external pressure. Internal pressure depends on the number of collisions with the inside wall of the container. So let's go back to that Coke can that was left in the trunk on a hot summer day. There's going to be a lot of collisions with the walls of that container, with the walls of that can. Now, external pressure is due to atmospheric pressure, the gases in the atmosphere that are colliding with the outside of the container. So, atmospheric pressure is very, very interesting. There is much higher pressure at sea level, like in New Orleans, as compared to living up high in the mountains of Colorado. Much lower pressure there. There's not as much oxygen molecules, not as much gas molecules way up high in the mountains as compared to at sea level. This is why you can get altitude sickness for those of y'all who have gone skiing. And all of a sudden you find yourself very quickly out of breath, or you actually start feeling kind of sick to your stomach. And it has to do with this less amount of oxygen gas the higher up you go in the atmosphere. Now, you would have even higher pressure if you go below sea level. So if you are scuba diving, so maybe you don't go skiing, maybe you scuba dive, and you would feel a pressure on you that's even greater than those people at sea level in New Orleans. Now, this also has some pretty interesting applications in terms of cooking. Atmospheric pressure also affects the boiling point of water. So you actually have to, you have to get the water hotter at sea level as compared to cooking, let's say, well, maybe not up in a plain, but let's say up in the mountains in Colorado. So this actually affects things. So sometimes if you buy like a cake mix, it'll tell you if you live at an altitude of such and such or above, then you should turn down the temperature of your oven or cook your cake for less amount of time. All right, so that is your lecture for today on kinetic molecular theory and how kinetic molecular theory ties in to temperature, the flow of heat, pressure, all of our different measurements for pressure, how to convert between those different measurements of pressure, and internal versus external pressure. So what you need to do now is go through, answer this worksheet. Notice that you also have a link here to something called blend space. This is something that Mrs. Boudreau put together. There's lots of videos here that might be able to help you better understand the lessons for today. So you have lots of questions to answer, and once you have this done, you need to submit it to Moodle. This worksheet is going to be due next Tuesday at 8:30 in the morning. Y'all have a great day.